All right. Let's do some hypothesis testing. Running it. Really? Really? Let's do some hypothesis testing today. Here's a quote from Sir Ronald Fisher, the guy who developed this system. A null hypothesis is never proved or established but possibly disproved in the course of experimentation. Every experiment may be said to exist only in order to give the facts a chance of disproving the null hypothesis. So it's pretty much like our courtroom. You are innocent until proven guilty. So, step one with our hypothesis testing is the hypothesis itself, what we did yesterday. A large city's Department of Motor Vehicles claimed that 80% of candidates passed driving tests, but a newspaper reported a survey of 90 randomly selected local teens who had taken the test found that only 68 who had passed. Does the finding suggest that the passing rate for teenagers is lower than the DMV reported? So we did this yesterday. My H null, my null hypothesis is P equals what?
0.8.
Very good, 0.8. And my alternative hypothesis is P in regards to what? 0.8. Less than. Right?
Yeah.
P is less than 0.8. So there I've established my hypothesis, my null and alternative. Now my goal is to disprove the null, either accept it or reject it. So again, like the court system, you are innocent. It is up to the prosecutor to prove that false. Step two is to model. Pick a model. Since we're talking about probabilities, our model will be the normal model. So are the conditions to use the normal model satisfied? Randomization condition, is this satisfied?
Yeah.
Yeah. Randomly selected. 10% condition, is that satisfied? Well, let's see, I selected 90. Would I assume that is less than 10% of the population of teens?
Mm-hmm.
That's a pretty good assumption. So that's satisfied. And success failure condition. Let's go ahead and test that. So remember that's NP needs to be greater than or equal to 10, and NQ greater than or equal to 10. So my N value is 90, and my P is 0.8. Is that greater than or equal to 10? So 90 times 0.8, I get 72. That's greater than 10. And then in Q, 90 times 0.2, so 80 minus 100, or 0.8 minus 1, times 0.2, that is 18. Whew, just barely. But that is also satisfied. So our success failure condition is satisfied here. We can use a normal model. Watch out. If your model step could end with, say this was 9, that is not greater than or equal to 10. Because the conditions are not satisfied, I cannot proceed with the test. If that's the case, stop and reconsider. You may want to use a different model then. So if we had failed, we would have to use a different model. Now we want to do the mechanics. Finding a p-value since we're using the normal model. Let's start filling in our variables here. N, that's my 90. P is my 0.8 and Q is my 0.2. What is my X value? What is my X value? Is that the 68 who passed? Okay. The number who actually passed. So let's plug these into certain formulas here. So since the normal model conditions are satisfied, we can use what's called the one proportion z-test. Let's find our p hat, which is x, 68 over n, which is 90. 68 over 90 gives me 0.7, let's just say 6. Let me find my standard deviation because I need that for my z value here. So it's the square root of p and q. So 0.8 and 0.2 all over n, which is 90. So square roots of 0.8 times 0.2 over 90. You should get 0.04, let's just say 2. And now let's find our z value. So our z-score. So the p hat, 0.76 minus my p, 0.8, divided by the standard deviation of 0.042. So 0.76 minus 0.8 divided by 0.042 gives me negative negative 0.95. We'll just put another number here, but I don't think that'll fit in the z table. 2. So now that I have my z value, I need to find my p value by using that z table. So it's a negative 0.95. And you would just plug that into the chart. Good news is, you don't have to do this all by hand. The calculator, what this value is, well, actually, we might as well just do it then. Normal CDF will give me this value as well. So sorry, I got a little ahead of myself. So remember, go to second var, so distribution, normal CDF. I'm looking for values that are, you told me, less than. So I want to go from negative infinity to, where am I at? There you go. Looks like with this example here, we might as well keep it. I round it a little bit further down. So 0.756 for my upper range, that's my p hat. My u, my mean is 0.8, and my standard deviation is 0.42. Is anybody confused about any of these numbers I'm plugging in? So I'm going from negative infinity to my p hat value, which is my x over n. Since we're using proportions, my mean equals my p, so 0.8, and we calculate the standard deviation is 0.042. So go here, hit enter, enter again, and I get 0.147. 0.147. So about 14, about 14.7%. Now, what in the world does a p-value of 14.7% mean? Well, that goes into the next step, our conclusion. So notice, we will reject a null if our p is less than 0.05. Was our p-value less than 0.05?
No.
0.05. Not 0.5, 0.05. It's not. So we cannot reject the null, which means we kind of have to accept it. So because the p-value of 0.146 is so large, we fail to reject the null hypothesis. These survey data do not provide sufficient evidence to convince us that the passing rate for teenagers taking the driving test is lower than 80%. If the passing rate for teenagers driving candidates were actually 80%, we expect to see success rates this low in about 14.6% of the sample size. This seems too likely to happen just by chance to assert that the DMV's stated success rate does not apply to the teens. So 14.6 is actually, as far as the statistics, a pretty high probability. We want to look at more like anything less than 5%. So we're going to accept, we can't reject the null. Meaning, we're not going to reject the fact that what they said, that they claim 80% pass the test, is false. We haven't proved that it's true, but we just can't prove that it's false. Does that make sense? Okay. It's kind of like you have been acquitted. Well, they didn't say you're 100% innocent. They just said they can't prove you guilty. Now, good news is the calculator can actually do this entire mechanics part for you. So instead of having to list this all out, find your p-hat, standard deviation, to find the z-value, to get a p-value, the calculator can actually calculate the one proportion z-test. And here's how it looks. You need to go to stat test number 5. So nicely it is labeled proportion z-test, which is what we're trying to find. So stat test one proportion z-test. Enter. Our p naught, so our thing we're trying to prove here with our hypotenuse is 0.8. Our x value, we found that to be 68, right? Number of people who passed. So 68. My n value was 90. And here's what you decide. What is your alternative? Alternative was less than 0.8. So when I go here, I need to put less than. And you can either draw the graph or just go to calculate. And notice it gives us our z-score, it gives us our p-hat, and more importantly, it gives us our p-value, 14.6%. Just like that. So it does the entire slide for us. That's what we're going to use today. The stat test one proportion z-test, number 5. That's going to help us accept or reject our null hypothesis. Now note, I talked about these vocabulary words. If it's not P, then that is a two-sided alternative. Because as we take a graph, our normal model here, here's where I reject. So if it's not this value, I'm going to accept everything else. So if it's not this value, I want all of this. Does that make sense? This is our two-sided. Otherwise, I'm going to have my normal model. And I'm going to have, just like in the last problem, our p-hat value here. P-hat. And I either want greater than this value or less than this value. In the case of the problem, it was over here. So this is a one-sided alternative. So there's the difference between the two and how they relate to calculator, how they relate to setting up our alternative. Looking at this problem. Advances in medical care, such as prenatal ultrasound examination, now make it possible to determine a child's sex early in pregnancy. There is a fear that in some cultures, some parents may use this technology to select the sex of their child. One study reports that in 1993, in one hospital, 96.9% of the 550 live births that year were boys. It's a medical fact that male babies are slightly more common than female babies. The studies also report a baseline for this region of 51.7% male live births. Is there evidence that the proportion of male births is different for this hospital? I'm going to give y'all a second to think about it. I want you to go through all the steps, come up with your hypotenuse, your null and alternative, then decide does it fit the normal model, and then use that one proportion z-test in the calculator to calculate your p-value to come to a conclusion. Is there evidence that the proportion of male births is different from the hospital? So the study also report a baseline for the region is 51.7. We want to see it if it's different than that baseline. So what is my H null or not? P is what? Equal to, what's my baseline? Yeah, 0.517. So I want to see, well, here's where I start, 51.7. And what is my alternative? No, it's gonna be the same. You're gonna use the same value as your.
Greater.
No, is it greater than?
Not equal to.
Pay attention to what it's saying. Is it different than this? Anything different will be anything that's not equal, right? So that is not equal. So what type of test was that? 2. Yeah, very good. A not equal is a two-sided alternative. So here's my 51.7. I'm taking anything outside of that. Now, let's go ahead and put in the calculator. Have it give us our p-value. So, I'll show it again. Stats, test, number 5, one proportion z-test. My p-naught is 0.517. What is my x value? Here's the stuff, my data that I'm working with. What would it be my x value? How would you calculate that? Multiply, right? Taking these numbers, I have 550 bursts. Multiply that to my percentage of 0.569. And we get 312.95, but the calculator does not like decimals with my x value because proportions, we are talking about people here. Can you have 0.95 of a person? No. So we'll go ahead and round that to a 3, 3.13. So again, don't put any decimals here for the x or the n. Doesn't make sense to have a partial of something, a partial vote. It's either all or nothing. And then for my n value is that 550. And since we are looking for any values that are different, we are using the not equal to. Go down here to calculate, and there we go. So there's my z value, there's my p hat, but the only one I really want to worry about is my p value of 0.0145. 0.014. Is this less than 0.05?
Yes.
It is less. So, the p-value of 0.014 says that if the true proportion of male babies were still at 51.7, then the observed proportion as different as 56.9 babies would occur at random only at 1.45%. I don't know why I'm being tongue-tied. Let me start that again. The p-value of 0.0146 says that if the true proportion of male babies were still at 51.7%, then an observed proportion as different as 56.9% male babies would occur at random only 1.5% of the time. With a p-value this small, I reject the null. This is strong evidence that the proportion of boys is not equal to the baseline for the region. Okay. So, luckily for us, we live in the 21st century and we have the calculator to help us calculate that p-value, right? Otherwise, as you saw in that mechanics part, it's a lot of steps.